Today, we're going deep into electric potential and potential energy, and we're focusing specifically on one particle, the electron.
Yeah, our mission today is basically to decode this for you, give you a shortcut, sort of to understanding what's happening with an electron's energy in this environment. We want you to leave feeling like you really get how its energy and potential change as it moves through this predictable electrical landscape. So picture this, a uniform electric field. Think of it like perfectly parallel lines, all evenly spaced. In our setup, the field strength, E, is 10 volts per meter. Nice round number. And the lines are 0.1 meters apart. And we'll be watching our electron move between three spots, 0.1, 0.2, and 0.3.
Okay, so you mentioned a constant electric field. What does that actually mean?
It absolutely simplifies things. A constant electric field just means the strength and the direction are the same everywhere in that region. This consistency is key because it lets us use a really straightforward formula for potential difference. We call potential difference delta V. And in this constant field, it's just delta V equals plus or minus E times D.
E times D. Okay.
But the D here is crucial. It's only the distance you travel along the field lines, parallel to them.
What?
If you move sideways, perpendicular to the lines, your potential doesn't change at all. It's like walking across a ski slope instead of skiing down it. Your height, your potential stays the same if you're just moving horizontally.
That's a great analogy. Okay, so D is only the distance along the slope or along the field lines.
Got it.
Got it. So knowing that, what's the next piece of the puzzle?
Yeah.
Especially since we're talking about an electron, which is, well, negatively charged.
Right, and this is where things get interesting. It's often where our intuition, which is maybe based on positive charges, can kind of trip us up.
Okay.
So normally we think moving with an electric field means potential goes down, like a positive charge rolling downhill, losing energy.
Yeah, that makes sense.
But the field direction is defined by what a positive charge would do. An electron is negative. It wants to go the opposite way.
What happens when our electron goes from point 1 to point 2 in this field?
All right, scenario 1, point 1 to point 2. The source shows this involves moving across 5 intervals. Since each interval is 0.1 meters, our distance D is 5 times 0.1, which is 0.5 meters.
0.5 meters, and that's along the field lines.
Yes. Crucially, this movement is directly along the field lines. So we use delta V minus ED because it's moving with the field.
Okay.
E is 10, D is 0.5. So delta V is minus 10 times 0.5, which is minus 5 volts.
Minus 5 volts. Potential dropped.
Potential drop. But now the energy. Negative charge times negative potential change gives a positive energy change gain.
Let's test this again. What about the trip from point 1 to point 3?
Okay, point 1 to point 3. Looking at the source again, this path covers 3 intervals along the field lines.
3 intervals. So D is 0.3 meters this time.
Correct. D is 0.3 meters. And again, this is the distance measured along the field lines. I know we keep saying it, but it's so important. Any sideways drift doesn't matter for potential change, only the progress along that electric slope.
Right. Reinforces the concept.
So the calculation is similar, since it's still moving along the field. Delta V is minus 10 times 0.3. That gives us minus 3 volts.
Potential drops by 3 volts.
Yep. And for our electron, moving to lower potential means...
Gaining energy again.
Gaining energy again. It gains 3 electron volts.
So summary, for 1 to 3. Potential difference made it 3 volts, energy change, plus 3 electron volts. The pattern holds.
It does. The change in energy in EV numerically matches the change in potential in volts, but the sign depends on the charge. Here, it's a gain because the electron is negative.
Makes perfect sense now. Okay, final scenario, let's flip it. What if the electron goes back from point 2 to point 1?
Ah, the reverse journey. This is great for seeing the symmetry. Point 2 back to point 1. It's the same path as 1 to 2, just backwards. So it covers the same 5 intervals. D is still 0.5 meters.
Still 0.5 meters. But the direction is different now?
Exactly. Now it's moving against the direction of the electric field lines.
Okay, so moving against the field, potential should increase.
Precisely. So our formula uses the plus sign, delta V equals plus ED. Plugging the numbers, delta V is plus 10 times 0.5, which gives plus 5 volts.
Goes 5 volts. Potential went up. It reversed the first trip.
It did. And now for the energy, we have our negative electron moving to a higher potential.
Higher potential for a negative charge means it loses energy.
Yes.
It's releasing that stored energy.
You got it. It loses potential energy. It loses 5 electron volts.
Minus 5 EV.
Minus 5 EV. It perfectly reverses the energy change from the point 1 to point 2 trip. The system is consistent, like releasing that compressed spring or letting the beach ball rise.
So for 2 to 1, Potential difference plus 5 volts, energy change, -5 electron volt. That really ties it all together. The direction, the potential change, and crucially, the electron's negative charge determining the energy change. Let's just recap the big takeaways. First, in a constant field, potential change only cares about movement along the field lines, not perpendicular.
Check.
Second, moving with the field drops potential, negative delta V.
Right.
Moving against it raises potential, positive delta V. And third, the absolute key for today, for an electron, negative charge, lower potential means more energy. Higher potential means less energy. The opposite of positive charge.
That's the core insight, yeah. That inversion because of the negative charge. And this isn't just theory. Understanding this is fundamental.
How so? Where does this pop up?
Everywhere, really. Designing circuits, understanding how batteries work, particle accelerators, even just basic chemistry involves how electrons move between potential levels.
Right.
It's all about how energy is stored and released at this tiny scale. Knowing these rules lets us predict and, well, engineer how energy behaves. It's foundational stuff.
Absolutely. These basics unlock so much else. So we focused on the electron gaining energy when potential drops. Here's something for you, the listener, to think about. What about a proton? It's got a positive charge. If a proton moved through these same scenarios, point 1 to 2, 1 to 3, 2 to 1, would it gain or lose energy as it moved along the field lines? And, maybe more importantly, why would it be different from the electron?